In this section, we'll look at the Fabian Neyer star removal method. This is a technique that he demonstrated many times over the past few years at various conferences. However, there doesn't currently exist a video that goes step by step through the technique in all of its full glory. So that's what I'm going to try to demonstrate now. Now, I need to very quickly add, of course, that all the mistakes that I might make and any misrepresentations of the technique that might occur, they're all my fault. It's my responsibility. Fabian is, of course, the ultimate reference, and I would encourage you to look at his materials that he does provide, especially through some of these conferences that he's attended. Now, in order to appreciate and really kind of go with the flow with this particular technique, I think it's important to understand what the goal of the technique is, especially in these kind of intermediate steps. It's very easy, I think, to get confused or lost when looking at the details of making star masks and other things that this particular method requires. So let me give you a high-level description of what the steps kind of look like, very, very, very general, and then, of course, we'll go through it. In fact, this will be kind of part one because I'm going to show you an easy example, and then part two will be a harder example. This could also be version 1. If I make too many mistakes, I'll need to go back and perhaps do this again. But let's see how far we can get. So the first thing that we want to do when we have an image that has something in it where we want to remove the stars, basically what we want to do is create a star mask. And I don't have that here because we're talking high level, but we need to create a star mask that basically covers all of the stars in the picture. That can be tricky, but let's say that we can do that. Now, having done that, what you want to do is look in the neighborhood, in the vicinity of these stars, using the multi-median transformation, and substitute sky values, that is, values that are background values, they're very near to each of these stars, into where the stars are. And that's what this image looks like. Now you might think, oh, well, that's it, I'm done. No, we can do a lot better. This is only an intermediate image, because the real goal is not this thing. This isn't really a very good approximation of what the background should be here. Instead, what you do is you subtract this estimate of the background from the original image. Now, areas where we didn't touch anything, they will just go to 0. That's all these black areas here. This is the difference of these two images. But when you subtract that little background value from these stars, you still end up with stars minus that little bit of sky value. And that means that these are corrected stars. They have values which approximately are going to be more like what they actually are, less the background and the whatever that local variation in brightness might be. So this is the goal. This is the thing that we really need to get. And ultimately, once we have this in hand, we can blur this image. We blur these stars iteratively and subtract this image from the original. And the stars will go away in the first step. Most stars will go away, and you'll actually end up with this image. When you subtract this from this, you end up basically with this. But you'll keep subtracting a blurred, slightly blurred version of this, and you'll be able to get rid of the halos of stars and any scattered light due to stars. So the interesting thing about this technique is that it is analogous to certain kinds of techniques that astronomers use to measure very faint signal, say the glow of gas and stars that are between galaxies. You need to remove the foreground star scattered light in order to make that measurement. And what we're doing here is something very, very similar. So once we've subtracted multiple times this image from the original, you end up with something that looks like this top image. You end up with mostly subtracted stars. A lot of the small ones just kind of disappear. But the brighter ones, because we subtracted multiple times, you end up with these dark little holes. Well, now comes the time that, like we did before, we want to fill with the local background, the local sky values, But because we have removed the star scattered light, the star halos, now when we calculate, we get a much better result, a much more, I don't want to say precise, but a better approximation of what value should go in for these stars, depending upon their neighbors, scattered starlight, and of course if they are embedded within the nebulosity itself. So that, of course, will, once you've filled them properly, will give you your starless image that you were after to begin with. So this technique is different than if we just did something that looks like this right off the top. We just make a star mask, we make all the stars we want black, and then we just look at the neighboring pixels. Well, if you do that from the beginning, like here, because of the glow of stars and their halos, you won't get the kind of result, and especially if it's a very crowded field, you won't get the kind of result that you can get when you use this full star removal method. So that's what I intend to show. Buckle your seats or whatever, and hang on, we'll get underway. Here's data that I hope will be easy to work with in order to demonstrate Fabian's star removal technique. I'm hoping it'll be easier because this is H-alpha data of M27, and what makes it perhaps a little bit better is that the stars are not so bright and their halos are greatly diminished in the H-alpha wavelength. Whereas if we started with, say, a luminance image, which is what I'll do in the next part, the challenges are a little bit greater. Regardless, though, the steps I'm going to show both here and later, they're all the same. It's just dealing with some of the challenges that makes it a little bit of a variation. So when first looking at an image like this, what is probably obvious is that if you're going to create a star mask to really capture all of the stars that you want to remove, it's going to be difficult to make it in one go. And generally, you're going to make more than a single star mask, so some star masks that get the bright stars, the dim stars, stars that are within the nebula, and stars that are outside. That's actually the distinguishing feature that I'm going to concentrate on to make my star mask. In fact, the technique that I'm going to do, I don't know, I'm not the total expert on this. If you find a method that is better than what I'm about to demonstrate, you'll probably get a better result in the end. So the better you can make your primary star mask, the better the star removal will be. So that is a true statement and something just to keep in mind. Spend time doing this thing, what I'm about to show. Now I'm going to use a technique that's going to capture as many stars as I possibly can, and that's kind of the decision that we need to make here. There are stars, in terms of a faint limit, that go all the way down to the brightness of the sky. And there are a couple of considerations. Yes, we can try to capture every single little faint star here, like this one right there. But when creating a star mask, once you get down to about the same brightness of the sky as a threshold, you'll tend to also, the mask that is generated using the star mask process, will also, make little blips where there are no stars at all. It's just kind of some noisy thing, and it characterizes it in that structure space. So the process that I'm talking about is the star mask process, and I need it to somehow get all of these stars down to a limit. So I'm going to do the best that I can. Now, if we don't get all of them, it's okay, because at the end, once we've removed the majority of the stars from this image, what's left over, just with a little bit of noise reduction, can go away. In order to get the star mask process to play with this well, the technique that I'm going to use is make this a nonlinear image. That is going to seed, if you will, the image in terms of structure space, so that this process will be able to pick up on things at the various scales, the structure scales, and we'll be able to get both, faint and bright stars and so on. So here is how it works. First, we need to make this a nonlinear image, and I'm going to go ahead and just use the automatic screen transfer function result here and just permanently stretch it. So we'll do that in the standard way here. Let's track this like that. and then apply that permanent stretch. Now, I really should do this on a copy rather than, I should make this a copy. Let me do this on a copy, because I'm going to make a mask out of this anyway. Okay. Next, one of the things that again helps the structure detection is to decrease the dynamic range of the image in terms of bright stars and things like that. What will be a byproduct of this is that the nebula itself, because we've permanently stretched it in this form, becomes a big contiguous object, much larger than a star. So when I apply the star mask utility to this permanently stretched image, the nebula will be a black area. We won't see any stars in there. That's why a second kind of star mask will need to take care of stars that are basically inside the nebula, at least appropriate for things that are inside the nebula. So the first part, though, is to do HDRMT. That is what is going to compress the dynamic range a little bit. So that's the trick. Make it a nonlinear image, and I'm just going to apply the default here and use HDRMT on the image, and then we can use the star mask to hopefully generate something reasonable. In order to save some time, now I can pause the video, but I'm going to save some time on my own side here. I'm going to draw a much smaller box of preview, and I'll just operate here on the preview to try to figure out what are the best settings for the star mask process. Now I know something. If I put my cursor here, I know the sky value looks like it's at about 0.2, 0.25. It varies, but somewhere in the 0.25 range. And some of the faintest stars, like this guy right here. I mean, what is that? So a faint star, might be 0.4, 0.3 to 0.4. That's a really faint star. A more typical faint star, now we're getting up to 0.6, 0.5, 0.7, and so on. So I suspect the range is between, maybe it's 0.55, 0.7, somewhere in there is probably the threshold that we want to set this at, because that's what some of those, not the very faintest ones, but just above the very faintest stars are. As a guess, I'll just use 0.6 as my first guess. Now, in terms of a scale size, I'm going to try 5. I'm not sure it'll get really big bright stars, but let's try 5 and see what happens. Large scale growth will do just a little bit. Small scale growth, I'm going to say no. We don't want to make the small stars, their bits of that mask, be any larger because they subtract relatively well. They don't have halos. So I'm not so worried about their size. And compensation, I'm just going to set it to 1. Okay, the smoothness. This determines, how round stars are in the mask anyway, how round our stars are going to look in the mask. But it also makes stars, especially the small ones, very gray. So I'm going to start with half here, see what we get. We want to binarize the result. And these would be the settings I'm going to try to apply here to the preview. And it's just a first stab at it. It's very likely we'll need to do just a few iterations to kind of tune it. All right, so we have something of a result here. Going to try to make these two images the same and then blink them and see what we get. So here we are. I'm blinking the images, and it's not bad. So what I notice is that if you look at some areas, like this little blip right there, right above my cursor, it appears where it doesn't actually exist in the real data. So we're very close to that threshold of, finding little noisy things that will show up in the mask as a star. And that doesn't really hurt us, but we don't want the field to be overly crowded. So the fewer stars we can get and still get everyone is the best is the optimal place we want to be. I note that some of the stars here are ever so slightly squarish, and I also note we are not getting the very brightest ones. They're not being included. So I'm going to include, I'm going to raise the scale here one more level to try to get some of these brighter ones. To take care of the roundness of the star, we'll increase this, I don't know, 11. And that threshold, well, we saw some things that were being introduced that really weren't important. So I'll raise it, just a little bit to something here. And with that, let's apply again. All right, this is looking a little closer. Let's overlay. I think I may still have the old one, though. Let's see, star mask 1, star mask. In fact, if we blink these two, that might be interesting. So this is what we had, and now with my change, you can see we got the brighter stars, and I'm not getting quite as many small blips, which really aren't terribly real. So those are the changes we just made. So I'm going to remove this one. And this is just a preview anyway. I do see, again, square stars, so if I wanted to do this one more time, and I guess I would put the smoothness basically back to the, right up to the default. So I'll do this again. It doesn't cost you any time because I'll just pause. Hang on. Well, I went ahead and applied it back to my smoothness of 8. I didn't like the other smoothness. So I have square stars here, but I think that won't be first of all, it's not a problem as long as you cover the stars. It doesn't matter what shape they are for this purpose. But they're going to round up anyway in the process of what we're doing. So I just liked how these stars looked. I went ahead and applied this setting then. This only applies to this data, so do it with whatever good settings you might come up with for your own data. I applied it to the whole image because that takes a little bit more time. And what you'll see is, of course, all of that solid, bright part of the nebula is completely black here, which is fine. We're going to create another little star mask to take care of that. But everywhere else, we have our stars, and this mask that we make needs to be absolutely binarized. So you'll notice here, of course, these very small ones, well, they have kind of a grayness to them. So I will bring out the binarization process here. Binarize. And I think that basically anything above 0 is what we want here. So some very small number should be good. Yeah, that should do it. I think you'll agree that that gets a whole lot of stars in this image. So we'll use this, but now we need to create a second kind of star mask, not on the HDRMT. Well, actually, I'll keep this just in case I need this for some reason. But going back to the original data, now we need to create a star mask that will pick up the stars that are in here and elsewhere as well, but they will probably overlap much of what we already have. So it's really the interior ones we want to capture next. Since this is a temporary thing, I gave it a new name here, just called it Star Mask Nonlinear. I'm not going to keep it necessarily, but for right now, we'll just hang on to it. I'll minimize it here. Now we need to create the mask that is going to give us stars that are in the bright bits of the nebula here. And I was zooming in to look at, in this linear image, what are the brightnesses of stars in the background, so I can make a good guess as to where I need to be to capture as many stars as I can without getting the nebula involved. The nebula won't show up easily in the linear image because you've got to remember this is the stretched version. In the version that's not stretched here, you can barely see the nebula or many of the stars at all. It's only when you stretch it that you see all of that. So based on what I was just measuring, it seems like a threshold of about, You know, it's going to be some small number. Very small number. So this is 0.003, and it's a reasonably bright star. But those are pretty small, and that might pick up on the nebulosity. So I'm guessing something a little bit more than 0.003. So maybe 0.005. Let's get out our star mask, and we'll give it a go here for a threshold. I'm going to again create I think the best way to do this is to create a preview that'll slice right through. I'm going to do that again. Let's see if I can do this. It'll slice right through the nebula, like this. So we can see stars that are in and outside the nebula, something like that. Make it a little thinner so it's not as much area. And we'll start with 0.001. So let's try that. 001. I think I said 005. Sorry. And the scale, we'll try the 5. Large scale, we can keep that. Again, the small scale, I know we want to be 0. Compensation, I think we had 1. Binarize. I know in linear, I know we shouldn't do much smoothing here, especially based on what happened when we binarized the other one. So let's look at this preview, apply, and see what happens. Okay, so here it is. And it's kind of hard to tell, but you can see that I think some of these chains of stars here, let's, why don't we make this, well, it's going to be hard to tell because I bet you this is right in the nebula. If I did the following, if I did that, we're going to see just white because it's right in the middle of the nebulosity. And even if I turn off the screen stretch, it's still hard to see what's going on. But I can make an educated guess that what's going on here is that's probably one of the diagonals of some of that nebulosity showing up in there. And I think that what that means is that our setting might be a little bit too low. Yeah. So I think that that diagonal there is the same as the diagonal that's showing up here, and that's really, those aren't really stars. So I'm going to raise this threshold a bit. I'm going to try to minimize that to the best of my abilities, basically. Now there might be some, but let's try 0.009. And let's see if we minimize it if we do it again. So this appears a little better. Let's see. I will drag this over here. And now it does look like I see 1, 2, 3 stars here, 1, 2, 3 stars here. Maybe some faint ones are just not showing up well here. There's a star here that's probably this one. Maybe it's still picking up a little bit of the nebulosity, but you know, that looks better to me. Let me move down to here, and I'll move this one down as well, because there were some bright stars, and I just want to see if it picked up on bright stars or not. So let's do a full screen stretch here of automatic screen stretch. There. And yeah, that's fine. So it appears to me that let's be sure we're looking at exactly the right spot here. There we go. Yep, yep. So these two are these two, this guy is this guy, this is this, and so on. So we are picking up relatively bigger stars. Just want to make sure we got big enough. There's another one up there. Yes, it did pick up that star. So I'll keep it with a scale of 5. I think the 5 scale looks pretty good. These are the settings then. This should give us the stars in the middle of nebulosity. So I'm going to apply this to the entire image and get that star mask. Okay, so here's the result. Let's close this. I have our new star mask and I put the old one behind it. So if I blink, this is what we're getting. And then, you know, maybe let's zoom in 1 to 1 here. And somewhere, well, it shouldn't be in the middle of the nebula, because you won't be able to see the difference. So I've got 1 to 3 here. Let's put this at 1 to 3 and blink. And you can see all the things that are in the nebula, not here, of course. Let's make absolutely certain they're matched. Yep. You'll see that there is some overlap in bright stars that are in both. Most of the dim stars are obviously coming from the compressed version where we seeded it to create that first star mask. I think that's pretty close to the best you can do. You can see there are some features here that are probably part of the nebula, but yeah. This is where expertise in generating a star mask comes in helpful. So the final step here to make our primary star mask is to put these two together. The easiest way, of course, is to use pixel math. And what we'll do is we'll take the maximum of these two things. So let's go to expression editor. We have I have star mask nonlinear. Oop, that's not in there. All right. So the maximum, comma, and the one we just made is star mask 2, because apparently I haven't removed the other things, which I'll do in a moment. And why don't we make this a new image? And this is the combination of the two. So this is what we're going to save as the primary star mask.